Okay, so this is another lecture on fixed end beams. I think it's just a single example. Someone has kind of commented that they like the examples and they don't like the theory. Well, I mean, what's valuable to you? I won't worry about it. It's more for the second module. The elective module next semester, you're going to get to a stage where the maths is going to get to a level where you're not really going to be able to learn it off by example. You're going to want to understand the concepts, and that's why you have to have the theory. The other thing is, you might notice in the notes, while like here I'm only doing 2 examples, there are more examples. So like, look here, there's a marking scheme, there's worked examples, and there's not that many, but there are a few throughout the manual, so do have a look if you're looking for them. Okay, let's see what we got. So a light beam of span 6 meters has both ends embedded in walls. Now when we see embedded in walls, we have to think fixed ends. Okay, at the point 2 there's a load, a point load of 36 kilonewtons. Between 4 and 6 there's a UDL, and the 6 goes to the end of the beam, so we won't have to turn that off. Either by solving the second derivative of bending moment equal to minus load per unit length, or otherwise express the bending moment in terms of step functions, RA and MA. Now we're not going to do the or otherwise. I mentioned in a few other videos, but we won't worry about it now. And then solve this to find the deflection. Okay, you'll notice in the exercises that there's further questions, and they're really for, I suppose the idea would be, if you understand the concepts, once you see this example, you should be able to drive on and do the other little parts of the question. So let me show you what I mean by way of an example. So here's a fixed end beam. Use the slope, like this is kind of conceptual questions. Calculate the bending moment at 50 centimeters. And the answers are there. And obviously if you have an issue and you submit it, we'll get back to you. Okay. So let's go. So first of all, I recommend drawing a picture of the beam, and it's fixed ends, so we'll draw those walls. It's easier for us to draw the beam not actually deflecting, but of course it is deflecting. And the distance, the vertical distance between how I'm drawing the beam and where it actually is, it'll be millimeters. Well, as I said, that's the deflection. Okay. So maybe just from this picture, we might just remark at this point that the slope is 0 at 0 and the slope is 0 at 6. They're big initial conditions. This one is a bit easier, but this one is very important. So the slope at 6, it comes out straight out of the wall versus simply supported, where the beam can have a bit of slope here. That's going to be very important. Let's draw our things. So x equal to 2, x equal to 4. Now I don't really mind how you annotate them as long as everything is coming out right. So like some of you might put 2, 2, 2, but for the way we're doing it here, it's probably better to put that 4 and a 2 there. Okay, we have a point load of 36 kilonewtons and a UDL of 72 kilonewtons per meter from here to the end of the beam. And as we said, if it goes to the end of the beam, you don't have to turn it off. Okay, so write down the loading function. A point load is a delta function. UDL, its magnitude is 72, turned on at 4, doesn't have to be turned off. So we need to anti-differentiate minus this twice to find the bending moment. So I might just write in here, just for space, minus the load per unit length. They'll both be minuses. Minus 36 delta x minus 2 minus 72 u x minus 2. So I'm being careful the whole time with the wx and minus wx. I know from teaching this for years that people have issues here. So if they try and go to minus wx, they mess up the signs in various different ways. I think you're just better off writing down the wx. So we're going to anti-differentiate minus this twice now. So this is equal to the second derivative of the bending moment. So if we anti-differentiate both of these, which is the same as this and this, we'll get a true equation. So the antiderivative of the second derivative is the first derivative of bending moment. The antiderivative of fixed constant anyway, minus 36. Antiderivative of a delta function is u function, x minus 2, fix the minus 72, and antiderivative of u function is square bracket, called the Macaulay bracket. Now I've written a 2 there, that's obviously wrong, that should be a 4. Yeah. Now the other thing is I'll be doing some scanning tomorrow. Well, sure, what day is today? It's actually the 16th of October, but sure, where are ye? Every time we antidifferentiate, we pick up a constant. Sorry about the dog, there's nothing I can do about him. Antidifferentiate again. Fix the constant minus 36. He might actually come in and interrupt us, and I'll have to put him on my lap. And sure, we might show him to you. So obviously all this working from home crap, look, we only do our best. Square bracket, antiderivative is square bracket squared over 2. Antiderivative of a constant RA is RAX, and we pick up a second constant at this point, which is MA. If we simply supported, we say that that's 0, but it's not true because it's there is a bending moment here, as you need to understand at this stage. That's what I mean by concepts. You need to understand that the wall itself actually applies a bending moment to the beam. Okay, so it says there, in the case of simply supported beam, you could actually find RA and MA at this point, but it's not the case in ends of X. We must carry around an MA and RA. So now we need to solve, so we've done the first bit, we have written m of x in terms of step functions, RA and MA. Now we must do the second bit, solve EI, their constants, times second derivative bending moment, of deflection, equal to bending moment. Now here's our bending moment, 72 divided by 2 is 36, and there's the rest of it. So we'll anti-differentiate 2 more times. So if we anti-differentiate, we'll fix the constant EI, and the antiderivative of the second derivative of deflection is the first derivative, otherwise known as the slope. Fix the constant minus 36. Antiderivative of square bracket is square bracket squared over 2. Fix the constant minus 36. Antiderivative of square bracket squared is square bracket cubed over 3. Fix the constant RA. Antiderivative x is x squared over 2. And antiderivative of MA is MAX. The constant at this point, when you go from here to here, is C1. Yeah. Right, and now we go again. Antidifferentiate both sides, fix the constant EI. Antiderivative of the first derivative is the original function. Minus 36 divided by 2 is minus 18. Antiderivative of square bracket squared is square bracket cubed over 3. Minus 36 divided by 3 is 12. Antiderivative of square bracket cubed is the power of 4 over 4. Now we've kind of explained this a couple of times. So fix the constant RA over 2. And then the antiderivative of x squared is x cubed over 3. Fix the constant MA, antiderivative of x is x squared over 2, antiderivative C1 is C1 times x, and we pick up another constant here, C2. Now in practice what you're going to be doing is you're going to say, no matter what beam you have in this module, this is 0. So that's in 7019. And you're going to say, if it's fixed ends, now you shouldn't do it automatically, because if you don't really understand what's going on, it's very easy to make a mistake. You should do the following. You have an understanding that C1 is related to the slope at 0. It's proportional to it. Now we will again summarize this because it's so important. So it comes out straight, so we know that the slope at 0 is equal to 0. And we know that C1 is proportional to the slope at 0. And if proportional to 0 means a multiple of 0, it's just 0. So C1 is 0. But we have to understand that's not true if it's simply supported. For simply supported, the slope here is negative. And so C1 is proportional to something negative. It's a multiple of something negative. It ends up being a positive multiple. It itself is negative. So this C1 being 0 is true only for fixed ends. It's also going to be for cantilever, but I suppose we haven't got to cantilever yet. So C1 and C2 are 0. So 4 unknowns is tough. RA, MA, C1, C2, but we've 4 boundary conditions. We've got slopes at either end is 0 and the deflections. So we know y is 0, sorry, that's y is 6, so the deflection here is 0, and the deflection here is also 0. So you can't have, like, it doesn't go below the neutral at the support. Okay, so as I said, if you know what's going on with C2, it's proportional to y of 0 to 0, so that's, we've explained this. We might just look at the tidy up. 18 over 3 is 6, 12 over 4 is 3. If you multiply fractions together, it's top, top, bottom, bottom. So it's RAX cubed over 6. Take out the constant RA over x. Similar story here. Okay, so what we have to use now is the 2 boundary conditions over here. Let's see what it says. So use these 2 conditions, boundary conditions, to generate simultaneous equations for RA and MA. Might have to make this a bit small because I really want to present my answer at the very end. Y of x is equal to. Maybe we can write it up the top. We'll see. Okay, so first thing we'll do is EI will work with the y of 6. So what I'm going to do is I'm going to substitute x equals 6 into this. I love the maths now, I have to say, but it'd be nice to be doing it in front of you. But sure, look, what can we do? And you should be starting to kind of, especially if you're going to pick the electives, start to get into the attitude that you like maths. Just going to tell yourself, because if you're going to be an engineer, you're going to want to like maths. Now, obviously, you can be kind of a technician, but if you want to go further in your career, you're going to want maths. They do use a lot of maths. Now, not always the maths that you learn in your actual course, but yeah, just start getting a better attitude to maths. Sound like a bit of an idiot, I know, but look, I'm kind of going through the motions on this, just subbing in the 6, I may as well say something. Particularly for those of you who aren't actually writing, but I have recommended writing, remember. Maybe I should just shut up. So I've got the C1x and the C2, but as we said, they're 0, so there's no point dealing with those. So now what are we going to do here? Well, this is EI times y of 6, deflection at 6, well there's no deflection at 6, the deflection all occurs strictly between 0 and 6. So this is EI times 0, so this is kind of something again that you want to understand. This, and if you don't understand it, you're very liable to make a really stupid mistake. So this is 0, and so EI times 0 is 0, and so you don't have to write that, but I want you to, when you write the equals to 0 here, I want you to understand what you're doing. So this is equal to 0, so this 0 is equal to this. I'm just putting the 0 over there, it's just easier. Now what I'm going to do is I'm going to form an equation in MA and RA. Now the things in the square bracket here are positive. Now you'll see in the exercises, like say if you wanted the bending moment at 50 centimeters, if you plug in 50 centimeters, which is 0.5 into either of those, you're getting square bracket of a negative, that's 0. You have to understand that. But here it's handy enough. So I'm going to calculate these two numbers. So I'm talking minus 6 by, don't put 6 minus 2 into the calculator. It's 6 minus 2 is 4, you know that. Minus 3 by 2 to the 4. So that's these numbers here, minus 432. Now I don't want that there, I want RAs and MAs, so I'm going to add that to both sides. Plus 432 to both sides, it gets rid of that. Now 6 cubed divided by 6 would be 6 squared, which is 36. And then 6 squared is 36 divided by 2 is 18. The numbers get a bit nastier here if, say, the span of the beam is 7. Or even 5 or 4. So if you want, you could use Kramer's rule once you form the equations. I don't really want to see rounding, but if you are, 4 significant figures. Okay, happy days. We have one equation here in R and MA. We actually, the second module next semester, if you pick it, we do lots on simultaneous equations with more than 2 unknowns, which is important for your structural engineering. The other crack, the slope at 6 is 0, so we're going to bang into this yoke. X equals 6, and we get out 0. So we get EI times y dashed of 6 equals. I'm just going to write from the previous page. So minus 36 over 2 is minus 18. Square bracket. So I'll let the slope at 6. 6 minus 2 squared. Minus 36 over 3 is minus 12. Square bracket 6 minus 4. And that's to be cubed. And I have RA over 2. And then it's x squared, which should be 6 squared. And then we're talking MA x MA times 6. So like you have to understand that this is true for any value of x between 0 and 6. So if you sub in any value of x, particular 6, you get a true equation, so the equals make sense. As before, now we won't explain it totally, but this has to equal 0 now. So we get another equation. I'm going to bang these numbers into the calculator. Minus 18 by 4 squared is 16. Minus 12 by 2 cubed is 8. Let's get 384. I'm going to add that to both sides. Six squared is 36 divided by 2 is 18. 6 by MA is 6MA. And then add the 384, that's gone. 0 plus 384 is 384. So obviously, like some of this is quite fast, but as I may as well keep reminding you, you can pause me and rewind me. Simultaneous equations, do whatever you want here. I think last time I divided this by 3. I don't think that's nice now. Or maybe I divided by 2. Yeah, happy days. So I'm going to do this divided by 2. And maybe I'll just kind of call this equation A maybe. Although I don't really like A because it doesn't matter. A. So we're going to do A divided by 2, or minus 2 even. So I can get a minus 18 RA. But it doesn't matter how you do it. Or multiply by minus half. Look, simultaneous equations. Minus 18 RA. Minus 9 MA. One thing you will be looking out for is a negative bending moment. We've mentioned this before, I think. 432 divided by 2, but it's negative minus 2 and 6. Add these yolks together. They add up to 0, so that's not really 3MA. Yeah, we're probably going to have to write the answer up the top. 384, what is it? 384 minus 2 and 6, 168. Get rid of that minus 3. I want to divide both sides by minus 3. So I have 56, and minus 56, because plus divided by minus is minus. MA is equal to minus 56. Throw that yolk into some equation. Into that yolk maybe. So what I'm going to do here, let's call this equation B. If you end up with the right answer, I'm not too concerned with this. Like you can see my notation, like as far as I'm concerned, this is really neat work. Like I'm labeling my equations. From my point of view, if you get the right answer and communicate the right answer, can communicate well, it doesn't have to be this good. Just whatever makes sense. It is important to communicate it. You are an engineer. Right, what am I on about? So I'm going to take B and I'm going to take away 6MA because I'm looking for RA, remember. So B take away 6MA. So if I do that, I end up with 18 RA. Take away the 6MA from both sides, like that's gone. And I get 384 minus 6MA, and MA is negative. Be careful with that sign. So this is equal to 384 minus minus plus 6 by 56, 720. And then you want to get the RA on its own. It's multiplied by 18. What is the inverse of multiplying by 18 is dividing by 18. And so I get RA is 40. I'll just write into kilonewtons. It's worth making sure your answer makes sense. Your MA should be negative. What about that RA? Well, how much is, it's hard to say. Like there's 72, that's 144 plus 36, that's 180. So they have to add up to 180. It's probably worth looking at the shear over there and making sure that you actually get. So I'm saying there's 144 here, kilonewtons, 36 here, that's 180. So there's 180 between RA and RB. I found RA is 40. I'm just going to write that down. Is it true that RB is equal to 140? Question mark. So the RB is the shear at x equals 6. So I'm going to go to this yoke here and put in x equals 6. See what we get. Minus 36, u of 6 minus 2. So that's u of 4. Now if you remember the u, if you give it something negative, it gives you 0. If you give it positive, it just gives you 1 by 1. Minus 72, square bracket 6 minus 4 is 2. Plus RA is 40. So I think we're looking for minus 140 here. Yeah, bingo bango, job's a good one. So I suppose if you actually saw it in front of you, like it's really all of the, like 3/4 of the load is basically right near that support. It's going to be much larger. Very important, as I said, to present your answer. So we probably don't have space for it there, so we'll do it up here. What I'm going to do is I'm going to take this, I'm going to put the RA and the MA in. I'm going to divide both sides by EI. So my final answer is y of x. To get rid of the EI, I multiply both sides by 1 over EI. I have minus 6 square bracket x minus 2 cubed minus 3 square bracket x minus 4 to the 4. RA is 40 divided by 6. Now, like say 40 over 6 is fine, but it's equal to 20 over 3. I'm certain your engineering lecturers will change that into just 6.7. 6.6 is bad because it's 6.666. If you're rounding it to one decimal place, 6.7. And we've referred to it a couple of times. You're going to get away with that as an engineer, the rounding, due to factors of safety or factors of ignorance. But as a mathematician, I just can't write down 6.7. It's just really harsh rounding. If you really want to do it, I'd like to see 4 significant figures, 6.667. I think I would mark down 6.7. Certainly would mark down 6.6, even though it is okay according to your engineering colleagues, but I'm not using any, like this is theoretical, I'm not using any factors of safety or whatever. MA over 2 minus 56 over 2, what's that, minus 28? X squared. And there it is. So that's our fixed ends. As I said, there's a little bit of a marking scheme there. Now, for one question, I might just bring your attention here to the exercises. These are interleaved. Now, this is designed more for people who are going on to do exams. And what it's about is, it's just making sure, it's about putting revision in the exercises and also making sure that you read the questions properly. So like if you look, normally you'd say, oh, that's the fixed ends question, here's loads of fixed ends. Sorry, that's the fixed ends section, here's the fixed ends section. Oh my God, this is the fixed ends questions. But what that means is you're doing all your simply supported, then all your fixed ends, whereas you really should be able to do both at the same time, and ideally maybe do some simply supported revision while you're doing the fixed ends to kind of contrast, you know, oh, it's important, the MA is 0 for simply supported, but it's not for fixed ends. So if you look at it, you've got a combination of fixed ends, simply supported. It's very important that you read the question properly. And in general, that's very, very important. I don't think we've much else here, do we? Okay, we're going to go in our next lecture, we're going to talk about cantilevers.